Hey, AP Physics. I decided that I'm going to go ahead and put, for keeping the notes a little bit cleaner, I'm going to do a short video to explain to you the small angle approximation. World famous in physics, it is this small angle approximation. Now, it's kind of cool how this maps right onto what we're doing in calculus class. You know that the Taylor series for the sine function centered at at x equals 0 is this odd alternating function, right? And it converges everywhere. It's one of the ones it does. You can do the ratio test on that. How good is this approximation? And what if we want to actually use it in practice? And what if we wanted to do, because of the alternating series error bound, I know that the sine of x is approximately equal to, if I only just take the first term, it's approximately equal to x with an error. Since this is an alternating series, the error is not bigger than this. Error is less than x cubed over 3 factorial. So that's kind of cool that you could say, whenever you see sine x, you could say, oh, you know what, just replace the sine x with an x, because they're about the same as each other. That's fine if you stay pretty close to 0, right? If you start plugging in very big x values, then your error is going to get very big. So what we need to do real quick is just figure out, what are the x values that will give us an acceptable amount of error. So how much error do you think we want to have? Well, let's say I wanted my x cubed over 3 factorial. Let's say we wanted to be good to 2 decimal places. We want 2 decimal places of accuracy. Then I would need this next term to be less than or equal to 0.005. That's how we do 2 decimal places, right? Okay, so that would mean that my x cubed would have to be less than or equal to 0.005 times 6. I was going to do that with my calculator. I don't think that's necessary. And then I am going to take the cube root of that with my calculator, however. Oh, math. My cube root. I guess I could have just raised it to the 1/3 power. That works too. So that gives me about 0.31. So 0.03. So x is, let's say, less than 0.31. I don't like putting the equal sign there just because this is, okay, you can put the equal sign. It really doesn't matter. We're just trying to find a decent approximation. And this is all absolute value stuff, right? So the so that's going to be in between negative 0.31 and 0.31. Okay, so what does all this mean? It means that if you have angles that are in between 0.31 and negative 0.31, then you can, if 2 decimal places of accuracy is good enough for you, then you can just replace the sine function, sine x, with x, and it's good enough. And we're doing things like ignoring friction and air resistance, and so I think 2 decimal places of accuracy, we should be pretty okay with that. Now, what are these angles? These are, let me just summarize here real quick. So sine x is approximately equal to x for angles between negative 0.31 and 0.31. But these, recognize, are in radians. anytime you're doing calculus with trig functions, you have to be in radian mode. So just to get a sense, because in physics we often think about angles in degrees. What are these things in degrees? So 0.31, if I want to change that to degrees, I need to multiply by 180 and divide by pi, right? So that's about 17.8 degrees or something like that. So usually what we see for when we are cued or clued into the fact that we can use the small angle approximation and just replace sine x with x, it's often said that there's something that is in small amplitude oscillation. That's a hint to us. Go ahead and use the small angle approximation. The sort of rule of thumb about it is that the small angle approximation is good for angles or oscillation with amplitude less than about 15 degrees. Now that's a little smaller than this, right? But that makes it safer to use that approximation. In practice, when you need to use the small angle approximation, you just have to say, it's kind of like, you know, the situations in calculus where you have to say, I'm doing the ratio test. You just kind of have to announce what you're doing and say, like, by the small angle approximation, sine x is equal to x, and then you go from there. So that's pretty cool. Last thing I'll just show you real quick is if you go to your calculator and you put in two things. So the small angle approximation is this move where you take sine x and you just replace it with x. So let's look at those two things side by side. Let's make my first function equal. Actually, it'll be in the xy, so never mind. Well, I will put it here. Maybe it'll make it more clear. So let's let y1 just equal x, and let's let y2 equal the sine of x. And I'd like to look at the values for those things side by side in the table. So I'm going to go to table set, and I want my table to start at 0, and I want it to go up delta table by, let's say, 0.01. And I want it to go ahead and generate that table automatically. So let's look at it. So remember in y1, I put just x, right? And you can see, of course, those match up. It's where y equals x. So here's all those x values. And here in y2, this is the sine of that. Now, we're making a case here with the small angle approximation that these two things are close enough that I can just swap one out for the other. So 0.01, 0.01, you can see what's happening here. 0.06, definitely that rounds to, I mean, it's good to 2 decimal places, right? And we're expecting this to be good. Let's check in and see where we are here. So like 0.2, this is 0.198. That would definitely round to 0.20, so I'm definitely still good to 2 decimal places. Just never mind the sine function. Let's just replace it with that x value. Close enough. And we said that it was going to be good to about 0.31. So you can see at 0.28, I'm at 0.276. That's still going to round to 0.28. Still good. 0.31, I've got 0.305. That will still round to 0.31. And then you can see, there it is. The first one, 0.314. There's the first one at 0.32 that does not round correctly to 2 decimal places. And remember, that's about 17, 18 degrees, and we're going to go with the conventional wisdom that small angle approximation you can do when you're at 15 degrees or less of amplitude. So that's pretty cool. Calculus in physics class, and even Taylor series. I mean, come on, how awesome is that?